Welcome to this tutorial series on microprocessors and design. In this tutorial, we are going to be designing our registers. So this is the course outline we've been working with so far, and in this tutorial, we've gotten to the register design section. Alright, so we are going to be designing 8-bit registers for general purpose registers. Then we are going to design a 20-bit register for our instructions, and then a 4-bit program counter. Now, program counter is a special purpose register. Now, it's 4-bit in this case because when we're designing our instruction format, the addresses, source address and destination address, were all 4-bit wide. Okay. So when we talk of a register is just a collection of a collection or array of flip-flops. We use D flip-flops, D for data, D flip-flops for designing general purpose register, and then a flip-flop is capable of storing a bit. And so if I want a 100-bit register, I just use 100 flip-flops in cascade. Okay. So since we are interested in designing an 8-bit register, we are going to use 8 flip-flops in cascade. So there is an image of a flip-flop. So we have an input, we actually have two inputs. So we have data in and then enable. So the data we wish to store in the flip-flop is supplied here, and then the flip-flop latches onto the data when we enable or disable. And in physical implementation, usually this enable bit is connected to a clock source, so that data in the register can only change during the rising or falling edge of the clock, depending on how it's implemented. Alright, so we will come to the program counter later on. But for now, let's get into the software and start designing our registers. Alright, so I have Logisim up and running, so let's get to work. So I hope you are all already familiar with Logisim. Please, if you are not familiar with Logisim, I would recommend you to watch the very first video. In that video, I introduced Logisim, some of the basic features, and then how it is used. And so I'm going to assume that you have a good understanding of that. Alright. And so this is our main worksheet. We are not going to be working in the main worksheet for now. We will create additional worksheets and then store our work there. We will use this main worksheet when we actually need it. Alright, so I'll come to project, and then I'll select add circuit. And then I need to give a name for the circuit. So I'll name it flip-flop because we want to design our flip-flops in it. So flip-flop, and then I just click OK. Alright, so I'm in the flip-flop circuit. Notice this lens icon here. If I open this, the lens icon switches to the main. So I'm inside of the flip-flop. So we will be designing our flip-flop here. Let me bring it up. Where is it? Alright, so let's get to work. End it. Another end it. Not gate. I just copied and pasted. Okay, so it's time to wire. Let's see. Let me zoom in a bit. Okay. Alright, so we need an input which should be 1 bit. So this is our input here. 1 input for data and then 1 input for clock. So input for clock over here. So let me name them. So this should be data in, and then this should be enable. Alright, so let me connect them. Alright, so 1 input from here. Hold on, yes, I've made a mistake. So 1 input from here to the enable. Okay, and then 1 input from here to data, and then 1 input from here to the enable as well. And then let me have the output. So we have an output. Okay, so the first output here comes to the input of this AND gate. Okay, and then the second one too comes to the input of the second one. Alright, so let's test our gate. So we are done with the design. Let's select our POC 2. So I've selected 1, but I realize the output is not changing. It's still 0. Now for this output to change, I will have to enable it. So if I select 1 and then I enable it, you can see that the output has changed to 1. If I change it to 0, whilst it's enabled, the output will always change. So if I put it at 1 and I turn off the enable, I can toggle the input. You can see nothing is happening. Alright, so this is a basic flip-flop. We are going to use this flip-flop in cascade. So let me first label it 1 bit flip-flop. 1 bit flip-flop. Alright, so I'll click this guy here and then I'll edit it. If I decide to use this flip-flop in other circuits, this is how it's going to appear. So this is the sub-circuit appearance. So the output is going to be here and then the input will be here. I just want to add a text to it so that I know the kind of flip-flop it is. I'll just name it D, so that anywhere I use it, I know it's a D flip-flop. Alright, so that's it. So I'm going to create another circuit where I'm going to use 8 of these in cascade. Okay, I could just go ahead and then cascade this, but I think it's neater using the sub-circuit system. So I'll add a new circuit. So this is going to be a data register. Data register. Okay, and then inside of the data register I'm going to add a flip-flop. So I just click on the icon and you can see it here. We can test it again and see if it has the same behavior. Okay. Alright, and then 2 inputs. So let's see. So pushing 1 here and then 1 here, you can see it's changing. So it's working as expected. Alright, so we are going to use more of these in cascade. So I have 1 flip-flop here. I need 8 of them to get an 8-bit data register. So Control C, Control V, Control C, Control V. This is 4. So Control C, Control V. This is 8. Alright. And so basically what I want to do is that I want to be able to change their inputs, the input of all 8 flip-flops at the same time. And so to achieve that, I'm going to connect all their enables together, so that whenever I change the input, it's going to change for all of them. So I'm connecting all their enables together. Alright, and then for their output, I don't want the individual bits going out. I want to make this an 8-bit output. So I'm going to select 8 here. So this is going to be 8. Now let's see something. If I connect this directly to this, it gives me an error. It's saying that this is 1 bit and then this is 8 bits. The weights are incompatible. So what do? I need to combine these individual bits into 8 before I feed it to this output here. And to do that, I'm going to be using the splitter. Okay, so the splitter, the fan out should be 8, and then the bus width should also be 8. Alright, and I want it to face left, which is west. Alright, so I have this here, and so I have individual 1-bit inputs, and then I'm going to have 8-bit output. That is what the splitter does. Okay. Okay, so now I can connect it in peace, hopefully. Now, the red here is because the states of the flip-flops are indeterminate. So what I can do is I can just give it an input here. These are 1 bit, and then I can just toggle it to push it to a non-state. Sorry, unless I apply some data before. So this is also enable for all the flip-flops. Enable. Alright, and then I need to give it an input data as well. So I'm going to have an 8-bit input data. So the label should be data in, and this is going to be, let me move them to the right. Okay, so I'm going to make this 8-bit as well. 8 bits. And then once again I'm going to use a splitter to combine, to actually split this data into individual bits. And so I'll just copy and paste this, Ctrl V, then I'll rotate it. It should face east. And so in this case, the individual bits, bit 0 goes into, bit 0 goes here, let me delete this. Alright, and then bit 1, alright, and I can push my data here. Alright, so now if I enable, then I'm going to have 0 0 at the output. So any bit I toggle here, I'm going to see the effect over there because it's enabled. If I should disable it, you can see that nothing is being changed. Until I enable it again, it's not going to take effect. Okay, so I've enabled it. You can see we have whatever we have at the input is the same at the output. So let's change the sub-circuit appearance of this again. Let's call this data register. No, let's just call it dreg. Okay. Let me enlarge this. And let me put this inside. Let me push this down. Let me move this circle. I think here it's good. It's good. Alright, so let me save my project. Let me save it. So let me save Rockson. Let me put it in documents. House materials. Let me put a new folder here. Okay. Then let me save it in here. So my file name should be registers. And then I click OK. Alright, so this is registers, data registers of registers. That's because we've opened the data register file. If I double click flip flop, you can see flip flop of registers. Yeah. So that's it for the data registers. If we need more bitrate, we just increase it. Now our instructions register was 20 bits wide, and so we are going to design that now. So project add circuits, I'll just call it IR, and then I'll copy and paste whatever is here. Okay, this is 8, so I'm going to add more to it. Control C, Control V. So hopefully this is 16. So I'll just copy 2 and then add Control C, Control V. Alright. So let me wire things again. Right, so I have to increase the width of this to 20 bits. And I need to increase this to 20 bits as well. Okay. So I need to change the fan out to 20 and then the data to 20 as well. Alright, same for this guy. So bus with 20 and then fan out is also 20. Alright, so we need to do some more wiring. Let me clear this. Alright, so wiring is done. Let's go ahead and test it. Oops. So Logisim was, sometimes it misbehaves, so all you need to do is just save your work and then restart the application. Okay. Alright. Alright, so let me just save and then restart it. So let me open it again. Recent files, that is registers. So let me go to IR. Yeah, so now things are behaving predictably now. Alright, so if I enable, the output is 000. So any change I make here, you can see its corresponding change at the output. Now if I disable and then I make any change, it's not going to reflect, okay, unless I enable. Alright, so that's it for register design. Let's see the next one here. The next one is the program counter. But we won't be designing the program counter in this session because it involves some additional components. So here we have a simple data. Okay, so we've designed a 5-bit register for the program counter. Okay, I can see we have an incrementer here. An incrementer is an adder circuit. We are going to design other circuits at the ALU design section, and so in this video we will just design the 5-bit version, and then we will come back to this diagram later on. Alright, so you can just practice the 5-bit version at your desk so that we won't have to do it in this video. Alright, so if you have any question, kindly leave it in the comment section. Thank you very much. See you later.